In November 2022, the world woke up to artificial intelligence. Within months, every major technology company on Earth was scrambling to secure the same chips from a company most people still dismissed as a gaming supplier. But NVIDIA didn't stumble into this position. The infrastructure behind the AI revolution was quietly built over 2 decades, through decisions no one on Wall Street noticed until it was already too late. In the late 1990s and the early 2000s, NVIDIA's public face was defined by the relentless march of gaming technology. The GeForce 256, launched in 1999, arrived with bold claims: the world's first GPU capable of processing 10 million polygons per second. Magazine spreads and television ads painted a picture of raw speed and visual power, promising players a new era of realism. For analysts and investors, the story seemed simple. NVIDIA was a gaming chip company, riding the explosive growth of PC and console markets. Revenue reports reinforced the image. By 2005, nearly 80% of NVIDIA's income came from gaming GPUs, with the GeForce brand holding a dominant share among enthusiasts and OEMs alike. Each product cycle brought faster chips, higher frame rates, and a steady stream of cash. Quarterly filings told a story of growth fueled by entertainment. In the first quarter of 2006, the company posted $583 million in sales, over 200% higher than the same period just a year before. The press pointed to blockbuster titles and console partnerships as the engines behind these figures. Sony's decision to use NVIDIA Silicon in the PlayStation only deepened the impression. This was a company built for gamers, judged by its ability to win benchmark wars and secure licensing deals. Behind the scenes, however, that torrent of gaming revenue was quietly underwriting something far less visible. Every new GeForce release demanded deeper engineering, larger teams, and more advanced manufacturing. Investors saw a cycle of games and graphics, and they missed the compounding effect. A foundation of talent, intellectual property, and silicon expertise growing with every generation, waiting for a purpose the market had yet to imagine. Jensen Huang's public image has always been careful, almost reserved, a founder content to let the GeForce brand speak for itself. Yet inside NVIDIA's walls, his ambitions stretched far beyond gaming. The language he used with engineers and partners was different from what appeared in press releases. In a keynote in 2008, Huang described the company's mission not as building graphics cards, but as developing compute as a platform. This was more than a slogan. It was a call to treat the GPU as the foundation for all kinds of computation, not just pixels and polygons. While the outside world focused on frame rates and console deals, Huang was urging his teams to imagine a future where their chips would power scientific research, data centers, and problems no one had solved yet. He spoke openly about the need for patience, telling investors that NVIDIA would accept lower short-term margins if it meant building the talent and technology for a broader platform. Quarterly earnings calls from this era show a founder willing to defend heavy R&D spending, even as analysts pressed for higher profits. This was a rare stance in Silicon Valley, where most CEOs chased immediate growth. Huang's patience set a different tone. He described the company's cash flow from gaming not as an end, but as fuel for something larger. The internal message was clear. Every dollar earned from graphics was an investment in a future where NVIDIA would no longer be defined by games alone. The result was a culture built for the long game, one that could withstand years of skepticism while quietly laying the groundwork for a new kind of computing platform. A graphics processor is often compared to a superhighway, but the reality is even more intricate. At the heart of every NVIDIA GPU lies a dense grid of thousands of tiny cores, far more than the handful found in a typical CPU. Each core is designed to handle a small piece of a much larger problem, like a city where every block lights up to tackle its own task. In this city, the work isn't handed off one job at a time. Instead, thousands of jobs move together, each routed through its own lane. This is parallelism in its purest form. Neural networks thrive on this kind of architecture. Training a deep learning model boils down to multiplying vast matrices, rows and columns of numbers, each calculation independent from the next. A GPU's streaming multiprocessors act like fleets of workers, each one multiplying, adding, and passing results along at the same moment. Where a CPU might process a single equation at a time, a GPU unleashes thousands, all in parallel, every clock cycle. But raw compute means little without the ability to move data quickly. That's why memory bandwidth matters. NVIDIA GPUs are engineered to shuttle gigabytes of information per second between memory and processing units. High bandwidth memory acts as a rapid transit system, feeding data to every core without delay. This combination, thousands of parallel engines and massive data throughput, makes GPUs uniquely suited to the demands of artificial intelligence, long before most realized those demands would ever exist. The result is a kind of invisible machinery, built for games, but perfectly matched to the mathematics of modern AI. The hardware foundation was hiding in plain sight, waiting for the right software to unlock its true potential. CUDA arrived in 2006 as more than a software toolkit. It was NVIDIA's invitation to a new world. For the first time, researchers and engineers could write code that ran natively on GPU hardware, bypassing the tangle of graphics APIs and assembly language that had kept high-performance computing out of reach. CUDA's design made parallel programming accessible, letting scientists describe their problems in C, then launch thousands of calculations at once across the GPU's grid of cores. This shift turned the graphics chip into a general-purpose engine, not just for images, but for any workload that could be split into pieces. The impact was immediate. Libraries like QBLAS and later QDNN became the backbone of scientific computing and deep learning. QBLAS translated dense linear algebra into pure speed, while QDNN delivered hand-tuned neural network operations that powered the first wave of modern AI research. These libraries offered more than raw performance. They lowered the barriers to entry. Developers no longer needed to understand the hardware in detail. They simply called familiar functions and let NVIDIA's code do the heavy lifting. This approach created a new kind of stickiness. Code, written for CUDA, ran only on NVIDIA hardware. And as more researchers adopted these libraries, the ecosystem began to reinforce itself. Universities around the world integrated CUDA into their curriculum. By 2010, hundreds of institutions were teaching GPU programming, and a generation of engineers graduated fluent in NVIDIA's stack. Open source projects, academic papers, and industry frameworks increasingly built on CUDA, deepening the dependency. The result was a software moat, one that protected NVIDIA's hardware led by making it the default choice for anyone serious about high-performance computing or AI. What began as a toolkit quietly became the foundation of a platform, locking in developers and research labs across the globe. The decision to invest in software, not just silicon, set NVIDIA apart from rivals who saw chips as commodities. With each new library and every university partnership, the company tightened its grip on the future of accelerated computing. When ChatGPT went public in late 2022, the world's largest cloud providers and AI labs responded with a kind of urgency rarely seen in technology. Headlines tracked a sudden race for GPU capacity as Microsoft, Amazon, and Google scrambled to secure the hardware needed for massive-scale training. Contracts were signed for thousands of NVIDIA H100 and A100 accelerators, orders so large that delivery windows stretched into the following year. Public statements from cloud executives described NVIDIA as the backbone of their new AI services, and researchers openly worried about bottlenecks and waitlists. The scale of demand outpaced anything the hardware industry had prepared for. In this moment, the hidden infrastructure built over 2 decades became visible in a single, undeniable way. Every leap in AI capability depended on a supply chain that ran straight through NVIDIA's factories, contracts, and silicon. The world had grown reliant on a platform few had noticed until the scramble began. Dependence on NVIDIA runs deeper than any single product or even a single breakthrough. Three pillars, hardware, software, and supply chain, work together to form a kind of lock-in that is difficult to escape. The hardware offers unmatched performance for AI workloads, but it is the software layer, especially CUDA and its libraries, that quietly binds developers and companies to NVIDIA's platform. Code written for CUDA does not travel easily. Switching means rewriting, re-optimizing, and accepting a performance hit. Meanwhile, long-term partnerships with chip foundries and memory suppliers guarantee that NVIDIA can deliver at scale when demand spikes. These compounding advantages have not gone unnoticed. Industry observers and regulators are beginning to question whether such dominance can persist without scrutiny. The result is a self-reinforcing cycle. Every new AI breakthrough increases reliance on the same stack, making it harder for competitors to catch up or for customers to leave. Today, the world builds its future on invisible foundations set decades ago. As power shifts from ideas to infrastructure, those who quietly shape the tools beneath technology decide which possibilities become real. In markets and in history, patience is the rarest and most decisive form of vision.